gonna see on the calendar.
Right, just the one.
Okay, I'll have to get that.
We're on film.
Okay.
All right, thanks for coming tonight, everybody. It's the last Wednesday night of the lab in 2022. When we resume, the days will be getting longer because we're going to take off next week, which is the solstice, and a week after that, which is the Wednesday between Christmas and New Year's. And then we'll be back on January 4th. And Molly Zeller from the DNA sequencing lab here is going to reprise the talk that she gave recently at Cold Spring Harbor Laboratory on Long Island in New York. So that's how we're going to kick off the year for 2023. What's that?
DNA sequencing?
Yes, yes. I wonder if I misspoke. I've been known to say the wrong thing in the wrong order, and that's not good with DNA. Oh yeah, I'll stop now. By the way, this would be a really good Wednesday to go to the library afterwards, because he's going to tell us about rockets and their red glare and not bursting in air. So that'll be great. We hope. Yep. So welcome everybody to Wednesday Night at the Lab. I'm Tom Zinnan. I work here at the UW-Madison Biotechnology Center. I also work for the Division of Extension Wisconsin 4-H. And on behalf of those folks and our other co-organizers, PBS Wisconsin, the Wisconsin Alumni Association, and the UW-Madison Science Alliance, thanks again for coming to Wednesday Night at the Lab. We do this every Wednesday night, 50 times a year. Tonight, it's my pleasure to introduce you, Dan McCammon. He's a professor here in the Department of Physics, and he does astrophysics. Dan, I get to ask you the 5 questions. You've heard other speakers do this because you're a frequent Wednesday Night at the Lab person. You know that the rules are, the answers just have to be, they don't have to be true, they just have to be believable. Where were you born?
California.
More precision, please.
Los Angeles.
More precision, please.
Don't know.
Oh, wow. That's good.
Yeah, nobody told me.
Where'd you go to high school?
I went to Hawthorne High School in California.
Very good. And then where'd you go for your undergrad and what did you study?
I went to Caltech and ended up studying physics.
And then where'd you go for your advanced degrees and what'd you study?
Well, they let me in here, so I came here for grad school.
Good. Anytime anybody comes from LA to Madison, I always wonder if the major draw was the ice fishing.
Oh. Well, fishing here is good, but I have not been ice fishing. That's never been a big attraction. Trout fishing is good here.
Yes, Black Earth.
And, yeah, that I did a lot of in California. So.
And then you spent a couple of years in Thailand?
Yeah. Just came off my first postdoc. My first postdoc was coming to an end. I had no idea what I was going to do next, and they offered me a job. So It sounded like fun, so I went.
What town were you in?
I was in Songkhla,
Okay.
which is far south, out in the boonies. It's about 40 miles from the Malaysian border.
Okay. Once again, not much in the way of ice fishing.
No.
Good. And then when did you come here for your faculty position?
Well, fortunately, when it was really a dumb idea to go there, as my advisor kind of hinted, but my contract was just running out down there, and I got a letter from him saying he had a postdoc opening coming up, and would I be interested?
Great.
So I said, I don't have anything else to do, so yeah, sure. So I came back, and I guess 4 years after that, I got on the faculty.
Very good. So tonight you're going to talk with us about what is well, I got to look at it. What the heck is X-ray astronomy and why do we bother? Would you please join me in welcoming Dan McCammon to Wednesday Night at the Lab? Thank you.
Well, I'd like to start out by showing you the people who actually do the work. I have what's called a single investigator group. It's fairly typical in the physics department. So it's just me, 1 postdoctoral scientist, 4 graduate students, and 6 or 7 undergrads. So what we do is X-ray astronomy. And when people ask me, well, what's X-ray astronomy? And I say, well, you look at X-rays that come from things in the sky. And you get this kind of funny look. And this is obviously what they're thinking. And I say, no, this is not an X-ray. This is a radiograph. It's a piece of film. And the X-rays are the things that the radiation that goes through your flesh and hits the film and turns the film black. And this is just the same as an old-fashioned film camera. The light comes in, the light hits the film, it turns it black. And that's not coincidental that those are similar, because X-rays are just another kind of light. This is something we call electromagnetic radiation, and it's really all the same thing. It's electric waves, electric field that moves through space at the speed of light. This all goes at the speed of light. And the only thing that changes along here is the wavelength. And it changes by a lot. This is maybe a mile long over here. And down here, it's angstroms. We're actually going, this is a logarithmic scale, so we're actually going by 17 orders of magnitude across here. And we call it different things in different parts. In the middle here, wavelength, a little half a micron or so, we call it visible light. And we can spread out the visible light a little bit here, and we can see that at the high frequency end, I guess I should say that there are different ways of talking about this wavelength. We can talk about the wavelength in feet or meters, or we can talk about how fast the crests go by moving at the speed of light, and that's the frequency, which is the scale down at the bottom here. And then also, it turns out that if you look closely at light, Einstein pointed out that, well, it really breaks up into little separate particles. And the energy in each particle is proportional to the frequency. And so this is another way you can talk about it, is what is the energy in one photon. And for visible light, that ranges from 1.5 electron volts up to about 3 electron volts, about a factor of 2. And an electron volt is about the energy an electron would get going from one end of a flashlight battery to the other. So it's a pretty small amount of energy, but this stuff down here is even less. So down here, these photons are so tiny, so low energy, that nobody ever thinks of them individually. You just think about the electric wave. Light, you can kind of go either way. The modern cameras with their CCD detectors in them actually see individual photons. By the time you get up to the gamma rays, this is something you can detect it with a Geiger counter, and you definitely hear it one photon at a time. When you hear that click, that's one photon hitting the Geiger counter. And then there's another click when another one hits it, because each photon has a lot of energy. So in visible light, we'll stretch it out here, and you can see as we make the wavelength longer, we go from it looking violet through blue to yellow to red, and then we can't see it anymore, so we start calling it infrared. But if you hold your hand in front of a hot stove, which will radiate infrared radiation, you can feel it on your hand. And going the other way, you go from blue to violet, and then you can't see it anymore, but it's still there, and we call it ultraviolet. And that'll give you a sunburn. And if you keep going past ultraviolet, you get to what we call X-rays. And if you go past X-rays, you get to what we call gamma rays. And this actually keeps going and going. In fact, astronomers have been looked at gamma rays out to about somewhere off the end out there. And the radio astronomers look down here at radio waves, but we just keep, at this end, we just keep calling it radio waves. Out here, we just keep calling it gamma rays, don't change the name anymore. Now, lost my pointer here. There we are. Okay, so this gray plot here uses the scale over here. This is showing you how far down they can get through the atmosphere. So the white area is how far they can penetrate. So you can see over here in radio waves, they can come all the way to the ground. So you can do your radio astronomy from the ground. Your visible light is a pretty narrow range here where your eye is sensitive, but that's this little narrow range that can actually get all the way down to the ground. And this is the brightness of the sun outside the atmosphere. So you can see the place where our eyes are sensitive, so we call it visible light, is where the sun is the brightest and where the light can actually get all the way down to the ground. And whether you believe in evolution or divine creation, either way, this is probably not a coincidence. That we can see the light just where the light from the sun gets down to the ground. Now, this is the region we call X-rays. And the more interesting part of the X-rays are down towards the low energy end here, low frequency, long wavelength. And you can see they don't get very far at all. In fact, at the soft end here, they only come down to about 150 kilometers above ground level. And that says you got to put your telescope up above essentially all the atmosphere. So we got to put our X-ray telescopes either on a satellite, but satellites are very expensive, and we also use these little rockets they call sounding rockets that you shoot straight up. They go up about 200 miles and then fall down again. But you get 5 minutes to look around. And they're cheap enough that we can get one every couple of years. The grad students don't have to wait 20 years for the next satellite. But that means this is quite a bit more expensive to do it that way. Plus, it's hard to build the instruments for X-rays. Because the X-rays, you can see they don't go through much air. They certainly won't go through a lens. So you can't use lenses on your telescope. You have to use mirrors. But X-rays also won't reflect off a metal mirror this way. You have to have it grazing incidence. So it's really hard to make the mirrors. It's also hard to measure the energy of the X-rays. So the question is, if X-ray astronomy is so hard to do and so expensive, why do we bother? Because you could do optical astronomy and radio astronomy from the ground. And the answer is you see different stuff. So the rest of the talk here is to try to convince you this is worthwhile. But we have to get oriented first, sorts of things we're looking at, where they are. We live in a galaxy called the Milky Way, and since we're inside it, we've never really seen what it looks like. But this is a nearby galaxy that we think looks a lot like it, because we think the sun's a fairly ordinary spiral. The Milky Way that we live in is a fairly ordinary spiral galaxy. This is an ordinary spiral galaxy. So we look about like this. And the sun is about halfway from the center out towards the edge and right in the middle of the disk. So we're about here. And if you looked at this thing perfectly edgewise, you'd see this disk is quite thin and has this bulge in the middle. And we're in the middle of the disk out about here. So this is our only vantage point for looking at our galaxy as we look from here. And we can look in towards the center, or we can look out towards the near edge and up and down. And this is what we see from here. So this is a projection that's oriented. So along the equator here is the disk of the galaxy. So remember, we're not at the middle. We're partway out towards the edge. And the center here is looking in towards the center. So we're seeing all the way across the galaxy, lots of stars, mostly far away. So they blend into this white band here. This is looking out at the edges here. That point and this point are the same one. We've flattened out the sky here. So this is looking out towards the near edge. So there's not quite as much stuff out there. The disk's a little thinner than in here. All these dark areas aren't an absence of stars. They're where there's dust floating around between the stars and it absorbs the light. So these are the shadows from the dust. And this here and this way, these are looking up and down the thin way. So you pretty quickly run out of stars, run out of the galaxy, but the stars you do see are relatively close and therefore bright. So this is the view. Anybody know what you call this thing? Celestial equator. Well, actually, it's the galactic equator. Okay, and it's conventionally called the Milky Way, right? And how many of you have seen the Milky Way? Okay, that's the advantage of going with an older audience. If I asked the students in my class this maybe 3 or 4 of them hold their hands up because they haven't been out of town on a dark night and looked up. Okay, but the important thing on this is everything you see on this is a star, and they're all in our own galaxy. This is everything, this is actually a painting, but it's everything that's bright enough to see with your naked eye. And it's all stars, and they're all in our galaxy. You can, of course, see other galaxies. If you've got a good pair of binoculars, you'll be able to see other nearby galaxies too, but they aren't bright enough to make the grade for this map. So, you know, stars are nice, but people have been studying stars for 4,000 years. So let's see what the sky looks like in X-rays. This is the 55,000 brightest X-ray sources. There's no sign of the galactic equator there, except maybe there isn't as much of the orange stuff in there, and that's from absorption by stuff in our galaxy, because there are no stars, probably no stars in this picture. You can see stars in X-rays, but they aren't bright enough to make the grade here. 90% of the things on this map are supermassive black holes. They weigh between 1 million and 1 billion times as much as the sun, and each one is at the center of its own galaxy. Okay? And these are not even particularly nearby galaxies. They're galaxies of Z of 1 to 2, typically. So that means the light from them left when the universe was only half or less old than it is now. I should have told you that each galaxy has about 100 billion stars in it. So that's like 300 stars for every person in the United States. So if someone offers you to sell you a star that they'll name after you, you can turn them down and say, no thanks, I have plenty already. And then there are also on the order of 100 billion other galaxies in the universe as we know it. So there are lots of these stars around, but these are special galaxies. They have this big black hole in the middle. Actually, we think most galaxies have the big black hole, but these have a bunch of stuff falling into it. And that makes, the stuff gets very hot as it falls in, and it makes a whole lot of X-rays. If you get something up above 1 million degrees, it'll start making X-rays. And so these are between 1 million and 10 million degrees, and they make just the X-rays from these things are 100,000 times brighter than all the stars in the galaxy put together. So these things, which we call quasars, they're black holes that have a lot of stuff falling into them, are very bright, much brighter than a galaxy, and you can see them very far away. So they're nice for studying the distant parts of the universe. And the 10% that aren't supermassive black holes, they're mostly sources in our galaxy, and they're quite a bit brighter than the others, but the brightness is something that doesn't show up very well here. Here the color is the temperature. The blue ones are hotter. These local ones are mostly blue on here, and they are small black holes, like only 10 or 20 times as heavy as the sun, and neutron stars. And neutron star, here's a picture of a neutron star. This neutron star itself is too small to see on here, but in the middle of this white dot here, there's a neutron star which weighs maybe half again as much as the sun, but it's only 10 miles across. So it's really tiny. And this particular one is spinning around at 1,800 RPM. That's about the speed of your electric fan. So you can think of something that weighs more than the sun, but it's spinning around as fast as your fan goes around. So it's got a magnetic field that whips around, and it's whipping those electrons around, and that makes the X-rays that we're seeing. So this is an actual X-ray picture. So when we first started doing X-ray astronomy, people didn't expect there to be anything to see, because the sun only puts out about 1/1,000,000th of its energy in the X-rays, and we can see them because the sun's so close. But if you put the sun off at the distance of the next nearest star, with the technology they had at the time, there's no way they could see it. So they weren't bothering to look. But this guy, Bruno Rossi at MIT, said, hey, you know, if we look with new capability, maybe we'll find something. So he flew a rocket with X-ray detectors, and he started seeing these X-ray sources. And so other people looked too, and they soon figured out that these things are enormously bright. They're a trillion times brighter than the sun in X-rays, and no one had any idea what they were. And for a number of years, it took several years to figure out what they were, because it turned out they were all black holes and neutron stars, neither of which existed at the time. I mean, pulsars were discovered a few years later, and that's when they got tipped off, oh yeah, with a neutron star you could make an X-ray source. And the other thing, of course, is these quasars, the supermassive black holes. This is an artist's conception, because this stuff is all a little bit small to see, but the black holes there in the middle, this is a disk of stuff that's falling into it that's gotten very hot, so we made it red. So most of the X-rays come from this. It's also putting out these jets. So these things are really interesting to study, and this is what most X-ray astronomers look at. They like to study these bright neutron stars and black holes because they're really wild objects. You can imagine what the density of a neutron star must be. And the black hole, of course, has zero size, so it's infinitely dense. But what we're more interested in is cosmology. And what's cosmology? Well, it's sort of where do we come from and what's our universe like? And this is sort of your creation story and your universe. So every civilization has their own creation stories, their own cosmology, right? So you'd think, well, our civilization, though, had 300 years, at the turn of the 20th century, you'd think we had 300 plus years since the Renaissance. We've had the Enlightenment, we've got the scientific revolution. You'd think we'd be way ahead. But at the turn of the 20th century, we were not much advanced beyond where past civilizations have been with how much we knew about the universe. In 1900, there was only one observational fact, scientific fact, that was relevant to cosmology, which is the fact the sky is dark at night. And that wasn't really understood at the time, but some people realized this ruled out the most common model of the universe then, which was it had always been the way it is now. And it turns out that's not compatible with the sky being dark at night. Okay, in 1927, they discovered the universe was expanding. The galaxies are getting further apart. And now they have one number, how fast it's expanding. So we have advanced over that 27 years. Nothing much more happened for a long time. When I was taking freshman physics, my physics teacher said, you know, cosmology isn't really a science. They don't have any numbers. He says, just got back from a cosmology meeting, and it's the worst meeting I've ever been to. It was just a bunch of old guys sitting around speculating because they didn't have anything to talk about. Okay, in 1964, they discovered the cosmic microwave background. That is, the whole sky was kind of hot, not very hot, 2.7 Kelvin, but that said there was these photons that just filled the whole universe, and the whole universe had that temperature, except where there's stars and things that make it hotter. And almost immediately, the theorists said, if you had this hot gas, one thing it did was it said there was a big bang. The universe started out as a very small thing that was very hot and expanded and cooled. And they also said, well, gee, you know, the physics is fairly simple that goes on in this hot expanding ball, and there should be these acoustic oscillations in it. So we should see, instead of a uniform 2.7, we ought to see this little pattern of fluctuations. And this is a plot of how bright the fluctuations are, and this scale is how big they are. So this is about 1 degree, 1/10 of a degree, 10 degrees. And so they said, if you see these little wiggles, then we can tell a whole lot about what the universe was like. The problem was that these wiggles are about 30 microkelvin on top of this 2.7 Kelvin. So what we saw is no features at all. That's because at the time we could barely detect that this 2.7 Kelvin was there, much less look for part per million fluctuations on it. But at least we now had two numbers. And I remember thinking that, oh, these theorists, you know, we've got two numbers in cosmology, and to describe this takes dozens of numbers. It says, if we ever are able to actually measure these things, it's not going to look anything like this, and the theorists will have to start over. But instrumentation improved, and 30 years later, we can actually see there are some fluctuations. This subtracts off the 2.7, and this is what's left. And in this first mission, COBE, the Cosmic Background Explorer, most of what you see here is noise. But the noise is small enough that they can see the fluctuations are significantly bigger than you expect from the noise. So there are real features here. They don't know which ones are real, because most of them are noise, but there are extra ones. So that encouraged them to keep improving the instrumentation and make it fly another satellite. And now it's a whole lot better, and these fluctuations are essentially all real. And then the Europeans flew another one a little later, which is even better, and made a nicer map of it. And so you now generate that theorist plot out of this. How big, here's a big one, and there are smaller ones, and you just count them up, and by golly, it looks just like what they said. And we now have, you can get lots of numbers out of this, and you can tell lots of things, and they did tell us a lot. They told us what the universe was like, and it solved a lot of old problems that we had, like it seemed like the oldest stars were older than the universe, and it fixed that problem. It fixed a number of others. And the only downside was that you had to accept not one, but two tooth fairies to go with this. Okay, we've got now a perfectly self-consistent system description of the whole universe, but it requires that 80% of the matter in the universe isn't made of electrons and protons and all the stuff that we are. In fact, it isn't even any particle that's ever been seen in a particle accelerator. It's some strange particle that doesn't interact at all with light. It makes gravity. And this agrees with that, agrees with other astronomical observations which were made earlier, which says, hey, there's something out there we don't see that's making a lot of extra gravity. And now we know that it can't be ordinary matter that we happen not to see, that it's something else. So this is all some particle that isn't part of the standard model of particle physics. They've never seen it in the big accelerator at Geneva, not for lack of trying. And that comprises most of the matter, but then worse yet, 2/3 of the stuff in the universe isn't matter at all, but some weird form of dark energy that just keeps increasing as the universe gets bigger. And that actually has the opposite effect from gravity. Instead of pulling things back together and slowing down the expansion from this explosion, it pushes it out and makes it go faster. And that's now been observationally confirmed it's doing that. But now, being an observer, I'm going to just concentrate on the stuff that we can actually see, because we can't see any of this, but this we can look at. And we think there should be that much, and I'm saying, well, that's the only part that matters to an observer. So this is an observer-centric view of the universe, where all those little lumps and wiggles are telling us we've got that much normal matter. And the problem now is, whoops, what happened here? Oh, yes. And that's how much matter we see way back here near the Big Bang, when the cosmic microwave background all comes from way out, when the universe was only about 100,000 years old. And then we can see that much matter. And all these little clumps have higher gravity, so they pull the other stuff in and they get more and more contrast, and eventually you get it dense enough that it can start making stars and galaxies and things. And at one time, we thought that all that stuff ended up here. But now that we can actually be quantitative and add all this up, we discovered that, in fact, all the stars and galaxies and stuff that we can see is only about 10% of how much normal matter we think is there. So we only are seeing about 10% of the normal matter. So where's the rest of it? Well, that started to get answered near the beginning of X-ray astronomy. This is a visible light picture of a cluster of galaxies. Our galaxy happens not to be in a cluster. It's in a small group. It's only got a dozen or so galaxies in it. But these big clusters, lots of them are in these big clusters that have a few thousand galaxies in them. So every one of these things is a galaxy like the Milky Way. And people said, well, we know our galaxy has these neutron stars and things in it, and they're pretty bright. We ought to be able to see them here. And if we point our X-ray telescope at this, we can look at a lot of galaxies at once. So they pointed their X-ray telescope at that cluster. And yeah, you did see the X-ray sources in some of the individual galaxies, but what really knocks your eye out here is there's a huge ball of hot gas in the middle of the cluster. And really hot. This is like 50 million degrees. So it's way hotter than the quasars and things. And from its brightness, you can easily tell how much hot gas there is, how much it weighs. And it turns out there's about 8 times as much matter in this as there is in all the galaxies in the cluster put together. That is, most of the material in the cluster is in this ball of hot gas, which is so hot that it only shows up in X-rays, so nobody knew it was there before. So that suddenly increased our inventory of normal matter by about a factor of 6. So we now found about half of it. And so the question is, where's the other half? That's still missing. The theorists, of course, have an idea. They say this is their model of about 300 million light year cube here of the universe. And these are where gravity has collected this original explosion material down into these filaments, and where the filaments intersect, the density is higher, and there the stuff is collected. So these red and yellow spots are where it's actually condensed down into galaxies and stars. So the galaxies and stars are there, but about half the matter is still left in these filaments. So that's where the theorists tell it is, but in falling down into these filaments, it's gotten heated to about 1 million degrees. And at 1 million degrees, it's very hard to see, and that's why it's missing. In fact, you'd have to look in the X-rays to see it. It's only going to show up in the X-rays. The other place they think now, this is a more recent idea, is here's our galaxy, or any other galaxy. It's about this big. But we know now it's embedded in this very large ball of dark matter that came with it. And we know now we can look at the gravity from this dark matter, know about how much is there, and we look at all the normal matter in our galaxy, all the stars and gas down there, and it's only about 1/3 of our share of the normal matter that should have come with that dark matter. So they think the rest of it has gotten blown out of the galaxy and is probably still in this big ball here they call a circumgalactic medium. But nobody's seen most of that material. And again, that's mostly because it's also hot and hard to see. And these days, the theorists think that probably half the matter in the universe is at temperatures that is in the form of diffuse gas at temperatures of 1 million degrees or so, and it's only going to show up in the X-rays. So that's kind of what we're trying to do, is look for the X-rays. So how do we look at X-rays? Well, I'm going to give you an example of how we looked at them this last summer. Okay. This is a map of the sky in X-rays. This is a range of X-rays that comes from gas at temperatures between 2 and 3 million degrees. And so we see lots of 2 and 3 million degree gas around the galaxy, practically everywhere, in fact. But it gets brighter here. This color here indicates the brightness. And so there's this big ball of hot gas in the center. Right now it looks like it has a hole down the middle and lots of holes up here, but that's the dust and cold gas between us and the center of the galaxy is absorbing that out. Down here there's less absorption, so we think there's this big ball of hot gas here. And it fills the center 8,000 light years or so of the universe. At temperature goes from 1 million up to about 4 million degrees, and nobody's studied it very much. But we have a nice instrument to study it, and so we've been wanting to look at this. And the problem is this thing here is a little bit too far south to see from New Mexico, which is where we usually fly our rockets because there's lots of desert and rockets won't hit anything when they fall down. But this is too far south, so we've been waiting for NASA to find a launch site in the southern hemisphere. And this year they finally did. So this is how we spent our summer vacation in our group. So this is the place this Australian startup decided they were going to build a spaceport. And they could make money, they thought, by launching satellites eastward. This is up fairly close to the equator, so you get a big boost from the rotation of the Earth. A good place to launch satellites. They can launch them to the east across the bay here and get paid for it. But for us, the advantage was that you could launch them to the southwest here, and this is an Aboriginal controlled area. All this part up here is called Arnhem Land, and the population density is very small. And this company had a treaty with the local Aboriginal clan that was in control to build this spaceport there. And the only problem was we were their first customer. So NASA says, that's okay, we'll bring everything we need. All we want you to do is we have to be able to get to the site, and we want you to pour a couple of concrete slabs for us so we have a place to bolt down our equipment. And first we got delayed a year because they hadn't built a road yet. But finally they did, and this is the main road coming down from the coast. And the site, this is the launch site, which was just cleared out of the jungle last year. This is the default rental car up there, which is a four-wheel drive diesel truck with a snorkel. Because there are no bridges, you have to ford the streams. We were there in the dry season, so didn't really need that. We didn't cross anything more than about a foot deep. And then it has this flag so the other traffic can see where you are in this big cloud of dust that is always around you. Okay, so we get there, unpack. These are the grad students putting our experiment together. Our X-ray telescope is inside this thing, actually looks out the back end here. You can put this together with the rest of the rocket. NASA has this sounding rocket support group that procures the motors for us, and they also provide all the parts that everyone who flies rockets wants, like radio transmitters to send your data down to the ground, a pointing system that uses nitrogen gas jets to tilt the thing around and point it at the part of the sky you want to look at, and very important up here in the nose cone, there's a parachute, so you can get your experiment back. So we got that payload all assembled now. It's about this big around and about 22 feet long, and these are the final tests, and then we roll it out, take the motors and the payload out to the launch rail. So this is everything stacked up here. It's a two-stage rocket. This is the booster, main stage, and there's our experiments here, the rest of the payload's up there. So now you wait for nighttime, and then you send the thing off.
6, 5, 4, 3, 2, 1, go.
Oh, yeah.
Unfortunately, it was pouring rain that night during the launch, and so there was this cloud deck that the thing disappeared into even before the booster burned out. But the whole flight looks like this. We got this booster. Actually, the one we're using now is a Terrier. It's a war surplus ship-to-air anti-aircraft missile that the Navy quit using back in the 60s. And that burns for about 5 seconds, and then it just falls away. They let it coast for another 7 seconds to get it into thinner atmosphere before they light the main motor. And then that burns for 35 seconds. And it burns out at about 70,000 feet. So this is where about the altitude the Concorde used to fly. And from that point on, we're just coasting. But we're going a little over 5,000 miles an hour straight up. So it will coast on up to about 200 miles and then fall down again. Yeah, it's just like throwing up a baseball. It goes up slower and slower, stops, comes back down. We spend about 5 minutes above essentially all of the atmosphere. So that's our time to look around. So at this point, they fire an explosive charge that cuts the payload loose from the rocket motor, and then that added cold gas, the nitrogen gas jet system, turns it over, so we're pointed now up at where we want to look in the sky, and we just go around. And then when it comes down, they put it into a flat spin to try to keep any one side of it from heating up too much. And the drag slows it down enough that when you get back down to about 20,000 feet here, you can pop out a parachute without tearing it off, and it comes on down and you can get it back. Okay, so this is back in the blockhouse during the flight. The radio data gets piped into our computers so we can watch the data come down while the rocket's up there. And I think you can see from the expression on people's faces that it looks like everything is working, which is a big deal because they've been getting ready for this for 2 years, and I've been looking forward to it for longer than that. And there's so many things that can go wrong, but nothing did. So it all worked. And this is what we got. This is a spectrum of the X-rays. So this is the energy, the photon energy. So this is like the color. These are the bluer ones over here and the redder ones over here. And you can see they come in all these spikes. And each of these spikes is characteristic of some particular element. And in this case, it's characteristic of an element that has most of the electrons knocked off because this is in 1 million to 3 million degree gas. And so most of the electrons are gone. So this line here is from oxygen with 1 electron. This is oxygen with 2 electrons. This is carbon with 1 electron. These are sulfur, silicon, iron with about 8 electrons left on it. So by being able to identify all these lines, we can tell what elements are there, and that tells us maybe where this hot gas came from. So this is a quick look spectrum. It'll actually look better than that when they finished analyzing it. We'll get about, the lines will get about a factor of 2 sharper than that. We'll get rid of a lot of this background here, but we haven't had time to do that yet. Plus, the payload is still in Australia because NASA hasn't been able to find a shipper to bring it back yet, along with half of my lab. But of course, once we get through, well, we get to do a little sightseeing. And up to this point, we've managed to avoid any overly close encounters with the local fauna. So we braved this side road here to get out to the beach because we're quite close to the coast. So this was the route to the beach. And this it is, beautiful beach. And there are hundreds of miles up there of beaches like this that are quite competitive with Waikiki, except there's no one on them. This is Miriam, one of our graduate students, and she has this whole place to herself on a Sunday afternoon. And the reason for that is every beach up there has one of these signs on it. They call these things saltwater crocodiles, and it turns out they love people. And although they're called saltwater crocodiles, they're perfectly happy in freshwater also. This is a river up there. This guy has his eye on an ibis breakfast. What you can't see here is there are actually 3 more stalking that bird, but they're staying under the water. And there are lots of these things up there. They're typically 15 feet long, so you don't want to get this close to one unless you're in a big boat. Okay, we did try swimming this one spot in a river. This pool has a waterfall going out and a waterfall coming in, so we thought it was unlikely to have crocodiles in it. And that's Miriam testing the water for us. Okay, but back in the lab. This missing matter that we'd like to find, we think is hot gas, but it's very spread out and thin, and that makes it very faint, and we're not going to be able to see it in the 5-minute rocket flight. So we've been looking at this denser gas down closer to the disk of our galaxy. It's also interesting because we think it keeps the gas in the galaxy stirred up and slows down star formation, and is the reason we still have a galaxy that's making interesting young stars, is because the hot gas keeps things stirred up and slows down making new ones. So we've been studying that for some time, but with one 5-minute flight every couple of years, you say, well, we're kind of underemployed here. So what are we doing with the rest of our time? And the answer is we're trying to make better X-ray detectors. As I showed you before, here's what the X-rays look like from this hot gas, and we can tell a whole lot from looking at these sharp lines. We can tell what elements are there, we can tell what ionization state they're in. In fact, you can look at Doppler shifts and see how fast things are moving. That's important for when we want to look at these faint hot gas, is because it's got this bright hot gas in front of it, and it makes the same lines. So how are we ever going to see a little faint line under this very bright one? And the answer is, well, you look at one of those intergalactic filaments, they're some distance away, so the expansion of the universe redshifts the line, and it'll move it out a little bit from under this line. So if you put this guy over on the other side, it could be this line coming from the filament. And we can see it even though it's very faint because it's shifted out from underneath. And our problem, of course, one question is, NASA and the European Space Agency and Japan all have big X-ray observatories in orbit with nice big X-ray telescopes on them. They look at things for hours or days. Why haven't they done all this stuff? And the answer is they all use these CCD X-ray detectors, which can't measure the energy very accurately. So this is on NASA's Chandra flagship X-ray observatory, and that's the best detector that's up there. The others are similar, not quite as good as this, and you can see this is all smeared out. You can see these brighter lines, you can tell they're there, and roughly how bright they are, but you can't do things like look for red shifts or see all these faint lines from the less abundant elements. So we can't do any of this stuff with that kind of detector. And the detectors that are up there are CCDs. They're like the detector in your phone camera, and an X-ray comes in and it'll knock off a few electrons, and you can collect those electrons and look at them. And the higher the energy of the X-ray is, the bluer the X-ray, the more electrons it knocks off. So you get an idea of the energy for the number of electrons that get knocked off. But there are fundamental statistical fluctuations that says one energy photon gives you different numbers of electrons different times. So this is about the best you can do with a regular detector that looks at the electrons that get knocked off. So we started thinking a long time ago, actually it was an infrared astronomer at Goddard Space Flight Center that had the idea. He says, forget this charge stuff, looking at electrons getting knocked off and things. He says, let's just do thermal calorimetry. And a calorimeter is pretty simple. You've got an absorber here, something that will stop the X-ray and contain its energy. And then you just let all its energy turn into heat, and then you have a thermometer measure how much the temperature goes up, and that'll be proportional to the X-ray energy. And all the energy goes into heat, so you don't have any limit on how well you can do. This is a very old technique. Food scientists for a long time have been using these things they call bomb calorimeters. So they want to know how much energy can you get out of food. So what they do is, you've got this heavy steel container here, you open it up, you put a Big Mac inside, and you screw the lid on, you fill it up with high pressure oxygen, and then you fire a spark plug, and the thing goes boom, and it burns that Big Mac all the way down to water vapor and water. Excuse me, water vapor and carbon dioxide, plus the odd bits that are left over. And basically, your body does the same thing with the Big Mac. Much more sophisticated way. It doesn't have to explode it. It does it at low temperatures. But since you started out with the same thing and end up with the same thing, the amount of energy you get out is the same. So this thing tells you how much energy is in a Big Mac, and it's measured in calories. Okay, and we're doing the same thing with an X-ray photon. We can get the energy of the photon, which tells us the color exactly. The problem is, of course, that one Big Mac is about 800 calories, and one X-ray photon is about 1/10000000th of a calorie. That is, it takes 10 to the 21 X-ray photons to make a Big Mac. So this was a really dumb idea that's going to raise the temperature enough that we can actually see it. But it turns out that if you start out with the calorimeter really cold, and by really cold I mean a 20th of a degree above absolute zero, then this tiny fraction of a calorie will raise the temperature enough to easily see, and we can measure it. Now the next problem is, of course, a 20th of a degree above absolute zero has never been that cold in space. You remember, space is 2.7 degrees, liquid helium is 4 degrees. But the solution to that problem was just have a smart graduate student, and she taught herself mechanical design and thermal design, and she figured out how to put together a refrigerator that would get that cold, which actually lots of people did for the lab, but she could also figure out how to make it stay cold through a rocket launch. That turned out to be the hard part. So we put together her design. This is the refrigerator. It's built like a thermos bottle with many layers in it. And this is about 1 foot in diameter, maybe 1.5 feet long. And that's what goes inside the rocket. And we're still using her refrigerator from 25 years ago. We keep making better X-ray detectors to put in it. And again, the graduate students worked with a lab refrigerator to get the detectors working. This was our first effort at making them. And then these were the first ones we flew, pretty crude looking. These are the ones we flew in Australia, look much prettier, right? And what are we doing now? Well, that's the last time we're going to fly these detectors, because we'd like to look at the cool end of the spectrum. 1 million degree gas, it turns out, is really crowded with lines. And this blue line here has the resolution of the that's the resolution of the detectors we flew in the rocket, the best ones we've made so far. And you can see that they still blend the lines together. We can't see the individual lines, so we can't figure out what's going on in this 1 million degree gas. And actually, most of the missing matter is at temperatures more like 1 million degrees. 3 million degrees, a lot easier to see. So we've been working on these second generation detectors. So over in the Integrated Circuit Lab, over in the engineering campus across University Avenue here, they've got this facility where you can take a silicon wafer and do things with it. So this is a 4-inch diameter silicon wafer, and we have a whole bunch of different test arrays on it, all different kinds of detectors that use this second generation thermometer, which is superconductors, and is much more sensitive than the old ones. And with these, we're sort of in the lab now getting like 1 EV resolution results you can get with these. So that's what we need, is 1 to 2 EV. This is a close-up of one detector in that. So this is the thermometer, which is a little square here, and then that's supported on these little thin beams. That's to thermally isolate it so that this can heat up and won't cool off too fast. And while it's warm, we measure its temperature with this thermometer, and then the heat runs out down here and it cools back down to a 20th of a degree, and then we can wait for the next X-ray to come along. And for size scale here, why 1 human hair would comfortably hide that thermometer. And of course, eventually you'd like to have more than 5 minutes observing time. And we actually did help build an instrument using the same detectors that are on the rocket. They looks just like that one I showed you, except the pixels are smaller because they don't have to catch as many as at once. And this is now on a big satellite, and that's supposed to get launched early next year as a Japanese launch. But it'll have these detectors on it. They'll still be the first generation ones, but they're way better than what's currently in orbit. So this will do a whole lot of stuff, particularly for the black holes and neutron stars. So science is fun, folks. Thanks a lot.
Sandy.
On the graph you showed, what was the wavelength that was off your chart?
What's the wavelength that's off the charts?
Yeah.
Well, let's see if I can find my way back on that. Yay. Okay.
No,
So
No, you had a graph.
these are the ones you're talking about?
No, farther out. You showed the results of your experiment, and there was something off the graph.
In our experiment. Oh,
You had
the
everything-
tall peak.
Yeah,
Okay.
Yeah.
I missed the, you went vertically off the chart, not horizontally. Okay.
Yeah.
This one,
Yeah.
that guy.
Yeah.
Okay, that is a calibration line. Okay.
Okay.
We've got a little source there. We have a radioactive polonium-210 alpha source. We shoot the alpha sources into a little piece of aluminum, and that makes characteristic X-rays from the aluminum, which are at 1500 eV. And we use that to track the gain because we've just shaken this thing terribly. We get 20 Gs of vibration as long as the motor's burning, and things are still kind of stabilizing from that. We can keep it within a few millionths of a degree, but that still makes the gain drift enough to smear things out. So we have this source that shines on it all the time. It's a little higher in energy than the part we want to look at, so it doesn't interfere with it, but we can use that to track the gain continuously, correct the gain over the rest of the field. That hasn't been done, and is one of the reasons these are a little bit smeared out. But that's a calibration line. It's a source we carry along with us.
You're measuring the top of that, then.
It's just got way too many. This is the number of counts in each bin, and it's just got way too many to show on there.
Oh,
And that's because we have to get enough counts to actually accurately measure the position of that line rather quickly because the gain's changing. So we want to be able to do that every few seconds. So it has a fairly high counting rate. But it's not interesting scientifically, so we let it just run off the top of the chart. But I could replot that, and you'd get a peak that's shaped like this one. That would look the same.
Any other questions?
Dan, is NASA planning to use any of your calorimeters on future X-ray satellites?
Well, yeah, these calorimeters are baseline for every major X-ray mission that people are planning. They're supposed to revolutionize the field because now you can do all this extra stuff. So the next big one was going to be Athena, which is a ESA mission that the U.S. was going to provide the detectors for, but that was a flagship mission. That was sort of the replacement for XMM and Chandra, was going to be this Athena mission, which has a very big telescope and microcalorimeter detectors. And those would have been the second generation detectors. The Japanese beat them to it with this smaller satellite, which actually was originally supposed to fly 30 years ago. That's another long sad story. It's taking us much longer to get the things into orbit than we expected. This is actually the 5th try to put them in orbit. But it's ready to go soon. But it has an extremely small field of view, so it actually will not wipe out our sounding rocket stuff because it would take it, the mission is called CRISM, and it would take about 20 million seconds of observation to get these statistics because it only has a 3 arc-minute field of view. And we look at 60 degrees of sky, so we get a lot more photons in a short time. So that one's, CRISM is specialized, is intended for looking at black holes and neutron stars.
I suppose the equipment to keep things cold enough to do calorimetry, that's a major fraction of the weight of the whole experiment.
It's a major fraction of the power consumption because now they're using mechanical refrigerators. So the system on CRISM I'm familiar with, and that's about 400 watts to keep the thing cold. And it has 6 compressors on it.
Dan, this is a spectrum, right?
That's right.
So how do you figure out where lithium-1 is or iron-8?
Well, we depend on laboratory measurements.
And you can do those in the laboratory?
You can do them in the laboratory.
Strip all the electrons off except the last 8?
That's right. They have various different ways of making sufficiently hot things. You can blast a laser and generate a plasma that's at those sort of temperature. They have a thing called an E-bit where they have an electron accelerator and it shoots a high energy electron beam in, and then you put a low density gas in there and the electrons will hit the gas and knock stuff off it.
Interesting.
But there are way too many lines to measure, particularly down at that low energy part I was showing you where there's thousands of them. So you depend on the theorists to calculate. They use quantum mechanics and calculate it.
Right.
And unfortunately, that gets really labor intensive for those lines that come from the upper levels of elements with lots of electrons. It's easy to calculate the wavelengths for carbon with 1 electron. Just scale it from hydrogen. But these L-shell lines are a lot harder, and we found a lot of inaccuracies in the lab data from the astronomical
So iron-8 would have multiple peaks so that you
there are many different lines because iron's got so many electrons, it's got hundreds of thousands of energy levels. That's the problem. Way too many to go and measure them all, even too many to calculate them all. They calculate some and then they sort of interpolate where the others ought to be.
But what you're pointing out, iron-8 is iron-8 on here, right? Or is that still a...
Oh, you mean down to the left? The iron-8 it would be 8 with would be iron with 7 missing electrons.
Okay, because normally it's 15.
It's the leftover thing. It's the 8th spectrum. What they noticed was that if you had a flame spectrum from sticking your sample in a Bunsen burner, then you went to a spark spectrum where you jumped an electric spark through it, and then to an arc spectrum where you were putting a lot of current through it, you saw the spectrum change entirely. The one would disappear as you got it hotter, the next one would come in. There was no atomic theory at the time, it was all empirical. They had no idea why, but they called this the first spectrum, the second spectrum, the third spectrum. That's those Roman numerals. And after they knew a little atomic physics, they realized that, well, the first spectrum is the neutral atom, the energy levels of that. The second spectrum is after you've knocked 1 electron off. Now all your energy levels shift around and you get completely different lines. So, and each level has multiple lines. So this line is from oxygen 7. It's actually a nearby pair. But this guy, well, this one isn't hot enough to show it. But there's another line here, which is also oxygen 7. This is oxygen 8. And this is hydrogenic, so you would call that Lyman alpha. And we should see oxygen 8 Lyman beta on here too. Didn't label, I don't know why. Okay, so oxygen 8 Lyman beta would be here. Lyman gamma is probably too faint to see. But here's iron with missing 18 electrons out of its 26. So this is an iron nucleus, but it only has well, 17 I know. This one is missing 16 electrons, so it's got a neon-like collection of electrons. So it has a spectrum that's analogous to neon. They call it neon-like iron.
And that's the only thing it could be, iron there. Iron.
We're pretty sure because the line's bright and iron is the only common element that's that heavy. So we're pretty sure of those lines. Although iron 17 being neon-like, that's a very stable one. So a lot of the iron stays in that form. And so those lines are bright. And the ratio of them doesn't fit the theory. So it doesn't fit what the theory says it should be. So people are working on that. And in fact, I just saw a paper that came out last week. Somebody had a laboratory measurement that agreed with the astrophysical measurement. And so they're looking at, the people who do the calculations are back looking at that.
So when the sounding rocket goes up and you have your 5 minutes of peering into the abyss, do you send by Wi-Fi or some other way? Do you radio back the data? Or
Yeah, the
okay.
data is coming back on the radio transmitter. We're looking at it real time. Actually, we can't radio all the data.
Okay.
So there's onboard a trigger, and all the events that are certain brightness get sent back on the radio. We have a lot of dead time on that. So we have 6 SD cards on there that are recording the continuous stream of data out of each one. So if we recover the payload, we can get those back. And so we've read those out. So we actually have the continuous output of each of there are 36 detectors in our array. And so we have the whole stream of data out of each of them, and we can process it much more efficient, but we get a lot more out of it than we can get out of the telemeter data.
Telemetric, okay, good. I couldn't remember the right word for it. And then how many gigabytes, terabytes, whatever you call it, are you getting in 5 minutes?
Well, not a lot. Our counting rates aren't that high, and so the SD cards, 36 detectors, we've got about 3 gigabytes total on that.
Okay. In 5 minutes?
In 5 minutes.
And each detector is the same. It's not specifically set up for a certain X-ray?
Yeah, the detectors are intended to be identical. They're all we calibrate each one individually. But yeah, they're all the same. And we have no optics. Our telescope is a hole that's cold, and we look out through it.
Yeah.
So the multiple pixels are just to get more collecting area.
Sure. Yeah,
And we don't want to do it with one big pixel, because then it would have a higher heat capacity, and we couldn't measure the temperature rises accurately.
Okay.
So once it tells you, once you figure out what elements are most common, I guess, what isotopes, what happens then? Like how do we figure out what it means?
How do we figure something out? Well, let me give you an example of one thing we could figure out. One thing, obviously, is we could measure the redshift, but these things are all in our galaxy, and the motions within the galaxy at this resolution, we can't see them, can't measure them, they're too small. If we had 1 EV detectors, we could measure the Doppler shifts, and we could see how the gas is moving in our own galaxy, and that would tell us something about, is this an expanding shell, or is it this static polytrope that's just sitting there? But as an example of what we're going to look, one of the first things we're going to look at on this is, if I go back to that map of the galaxy and what we're looking at, okay, so we can fit this distribution, once we account for the absorption, we can fit this distribution very well with what's called a polytrope, which is just gas sitting there and supporting itself. And that only has 2 free parameters to fit it, so it's pretty impressive that we can fit this whole arrangement. You pick a central temperature and density, and it predicts the temperature and the density everywhere else. And it fits that thing. It's not particularly physically motivated. We don't know where it would come from, but we know that the total amount of energy coming out is easily supplied by the supernovae, the stars that are exploding in that part of the galaxy. So it's at least consistent. It wouldn't be unreasonable. And the center of the galaxy is full of these old stars that explode and make type 1 supernovae. A friend of mine had another suggestion for this. He'd been mapping the spiral arms in the galaxy with an infrared telescope. And he says, you know, where's my pointer? Oh, there we go. Okay. He says, you know, there's this inner spiral arm that runs across in front of the galaxy about 3 kiloparsecs towards us. And he says, that spiral arm has star-forming regions in it, where there are a bunch of young stars, including very massive ones with short lifetimes. So there's all these supernovae going off, and they can collectively get the gas hot enough and moving fast enough that they can blow it out of the galaxy. And so he says, what this looks like to him is that you have star-forming regions in that arm, and they're blowing this gas out. And that could be made to fit this too. And the question is, which one is it? And I said, the center of the galaxy is full of these type 1 supernovae, which are low-mass stars. They're rather old, and they make a whole lot of iron. Whereas in star-forming regions, the stars are brand new. The only ones that are exploding are these very massive ones that have short lifetimes. And they are a different kind of supernova called a type 2 or a core collapse supernova. And they don't make much iron. They make a whole lot of oxygen. And so by looking at the oxygen to iron ratio, which you saw oxygen lines and you saw iron lines, so hopefully we can do this, we get an idea of we get an idea which of those models might be right.
Do they have to be mutually exclusive?
No, we could have a lot of hot gas floating around the center of the galaxy plus stuff floating out. And we might be able to tell the difference. Certainly, if we had an imaging telescope, or if we could look at multiple places along there. So if we had this thing on a satellite, so we had even hours to look, we could do that.
Yeah,
But it would take a whole lot of 5-minute rocket flights.
how do your grad students manage to get a whole, degree out of one rocket flight every couple of years?
Well, there's just all kinds of information in that spectrum that nobody else has ever had. And so they can say a lot about it. This was one question that they could answer, so one of them might, that's good, certainly good for a thesis, and one of them might do that. The other one would take one of the other questions and do it. Plus, they've also done a whole lot of other stuff that they could have written their theses up. These are mature graduate students. They're both 6th year, and they're really good. And when this thing got delayed, I said, you guys should just pick one of the things you've already done on the detector development side, and you could write that up for a thesis. But they didn't want to miss the rocket flight.
They didn't test it.
Yeah, and they didn't want to miss out on, they got to accompany the payload on NASA's C-130 on this 7-day island hopping trip across the Pacific, which I didn't get to go on that, but that must have been quite an adventure itself, because they went from Wallops Island, Virginia, to California, to Hawaii, to Wake Island, to Guam, to Darwin, to Gove, with the NASA crew on the plane. And they got to transfer liquid helium into our detector every day to keep it cold.
You mentioned before you started that you originally started with Nike rockets, and many of the people, most of the people in this room remember Nike rockets.
Yeah, the boosters, the booster they started using was a Nike from back in the 50s. The ones they had deployed around every city to shoot down the Russian bombers. We're now using a Terrier, which is this 1960s anti-aircraft missile from the Navy. And again, NASA gets those for free because the military doesn't want them anymore.
And what are they using for fuel?
They're they're made by thiokol, and the fuel is a mixture of what's basically artificial rubber and aluminum flakes and ammonium perchlorate is the oxidizer. And you just stir that all up and melt it, and then you pour it into an iron pipe, and you've got yourself a rocket. Although it's actually a terribly sophisticated thing. The Black Brant, the main stage, which is a commercial sounding rocket, we had one flight where that had a combustion instability, and actually it happened on a number of other flights. They tried redesigning the thing 3 times, and they think now they've gotten rid of this problem. But the combustion instability gives you, they think it's, well, they're not sure, still not sure what it was. But it makes the thrust irregular, and you can see it in the flight. You see all this stuff blowing out the back, and there were big chunks of molten aluminum that were stuck on the sides of the nozzle when they got it back. And it gave us 100 times the vibrational heat input. It was shaking so hard, and that we actually lost the temperature regulation on that thing. It got cold enough that we got data, but it wasn't quite as cold that the regulator would start working. So the temperature we just came into regulation right at the end of the flight. So the whole flight, the gain is wildly changing, the nonlinears change. Poor grad student who had that flight spent 2 years developing the software and the methods and doing all the calibrations on it. For a year later, NASA's still bugging me, can we call this flight a success? And I said, well, we haven't seen any lines yet, but we're still hopeful. A year later, we still haven't seen any lines, and eventually he got the lines, and then he not only recovered our full resolution, but he developed this new method of analyzing the data that we could get 3 times as many events out of it. He figured out, as part of this, how to analyze events that are overlapping. And so we got rid of the dead time that normally was costing us 2/3 of our accounts. And he went back and reanalyzed the previous 3 flights that way and got that much more data out of them. So it paid off, actually, having the problem, but cost him a lot of work.
And then how many, first of all, that's amazing math. And
Yeah, it's easy to spend a year working on 5 minutes of data.
And then, because I'm pretty fascinated by how much this solid rocket stuff, how many pounds or kilograms per second is this stuff burning?
Well, the Nikes, I remember the numbers, they were a little under 3,000 pounds of fuel, and they burned for 3.5 seconds. So gives you, let's see, our rocket that's sitting on it weighs about 3,000 pounds, and it's going at 12 Gs. So that's on the order of 30,000 pounds of thrust, right?
All right.
So that's why the thing, the space shuttle takes off, it's sort of 3, 2, 1, we have ignition, yes, it's starting to move, and then it clears the tower. This one you saw is 3, 2, 1, bang, it's up there.
Any other questions? If not, thank you very much. Illuminating talk. So we'll be taking the next 2 weeks off. We'll see you on January 4th, and I hope all of you can come join us next door at the library. Thank you very much, and happy holidays, Mayor, and Happy New Year.